All right. Happy Wednesday, everybody. We're going to continue with simulating a quantum computer in Rust. Last time, I was pretty excited, actually. I thought it was super cool to be able to optimize all the matrix multiplication as quickly as we did. I had certainly heard of sparse matrix multiplication before, but I expected the algorithms to be... I just never thought about it that much, and I had expected the algorithms to be more complex than they were. And so it was really nice to... I learned something, just learning the idea of a sparse matrix algorithm, basically being, let's, instead of computing based on each element of the output matrix, let's compute based on each non-zero element of one of the input matrices. That was a really powerful idea, I thought, and it was cool to be able to implement it as quickly as we were. So that was exciting. This time, I want to do some combination of a little more optimization, because I basically put in transformations back and forth from sparse matrices and algebra matrices, and I would, some of those are probably not particularly performant, should probably be rewritten, and then also I know that for sufficiently large inputs, even our stubbed out Shor's algorithm is hitting stack overflow, so we need to work out why that is, and probably allocate some things to the heap. So hopefully, I don't know, we'll see what I can get through today. But let's just start by, making sure all of our tests run. And let's take a look at... So this is the test of a stack overflowing. I think rather than trying to optimize the stack overflow, I'm going to try and optimize the rest of... Oh, right, this is the failure. Yeah, I'm going to try and optimize what's going on in the algorithm, and it could well be that by doing that, we just get rid of our problem. So let's take a look at what we've got going on here. So let's see where the slowness is. For now. So instantiating the matrices is pretty fast. Instantiating the identity matrix was not fast. That's interesting. So we can potentially take a look at that. Inverse quantum Fourier transform also not fast, but that's because we're inverting the Fourier transform, which I mean, maybe there are fast sparse matrix inversion algorithms, but that seems a little aggressive, and it wasn't super slow, so I think that's probably fine. Okay, and then adding gates is pretty slow. So let's find out what's slow about adding gates. I can't imagine that it's anything before this, so let's go here. Permutation is fast. Reverse permutation is fast. All this is fast, and then composing these big gates is a little slow, but it's okay. Okay, so this is actually pretty fast, because this is just multiplication. It's just that it's doing multiple things. It's just that it has to do a series of compositions. That's not so bad. Okay, so the only surprising one, really, was that constructing the identity was slow. So why is that? Okay. It's slow because when we construct the identity, we're using... Oh, is it? Self matrix. square matrix. So we construct a square matrix of size 1. Not of size 1. We construct a square matrix of size 2 to the... which uses a new unchecked. Interesting. So this might just be a case of... it being slow to... Okay, but we can make this faster. We can make this faster because we know how to construct an identity matrix without doing it via a D matrix. So let's do that. Yeah, this looks fast. This is what I would have written. I know it's superfluous. I like to write return. It helps me scan the function. Okay, so I think this should immediately be faster. Let's cargo test. Just make sure things are passing. Cool, seems like everything is most likely passing. And then let's quantum gate somewhere. We have a breakpoint we probably shouldn't have, don't we? Oh, right, add gate. Can't have a breakpoint in here. So let's debug this into this. Skip into. Whoops, that wasn't really what I wanted. Hey, that was a lot faster. Okay, cool. And that should speed up some other things as well. Nice. Okay. Speed up constructing identities. Where am I right now? Circuit refactor. Okay. All right, so that should be somewhat faster. Let's check out what else we can do in matrix to speed things up. So get is already nice. Identity now is nice. Okay, so all of our functions in sparse matrix are happy. It's the functions in square matrix that might not be. And okay, so new, oh, that's fine. Where's square matrix? Display almost equals. That's fine. Okay, so new unitary, we need this because I don't know how to calculate determinants from sparse matrix in an efficient way. Again, it might exist, and we already know that this isn't a particularly bottlenecky part of the code because we had to optimize it away previously. From vec normalize. Yeah, similarly, I need this to use unitary. Wait, do I? Maybe I don't. I'm not sure. Again, I'm not sure I care though, because it's not really a bottleneck. Identity is fine. One is fine. Permutations I already re-implemented using sparse matrices. Get is never used. Scale is never used. This is bad though. I just want this to be new unchecked. And self.matrix multiplied by a scalar. Well, yeah, I guess this is fine. The function's not even being used. It's fine. Okay, tensor product. So tensor product is an interesting one. Hey, Calcutten. How's it going? Do I by chance know Java? I have used Java. It is probably my least favorite language that's commonly used. I am certainly far from an expert in it, but I've used it in work contexts and a few hobby contexts, but I'm really not a big fan of it personally. Is that what you use? Did I just offend you horribly? Do I need to do... You hate it. Oh, good. Then I've not offended you horribly. What makes you need to use it? Am I super busy? Well, I'm the normal amount of busy, I would say. What's going on? Oh, you have to use it in uni. I mean, the thing is, it's not that different from other typed languages. Are there programming languages that you do like using and that you don't think you're, quote, trash at, unquote? I'm curious because I think it helps to, if you know what you do like, there are ways to kind of translate that into other languages. So, for instance, like if you've done a good bit of Python a good while back, but extremely basic. Okay, yeah, I mean, I love Python. Python's probably my favorite untyped language. Rust, which is what I'm using here, is my favorite language. Full stop, and in particular, it's my favorite typed language. And so, I mean, one thing that's very different about Java is that it's typed, whereas Python isn't. So in Python has what they call duck typing, where if you have a string and you try to add a number to it, that's a bad example, actually. What's a good example? Like, if you have something that you can call a function on, it doesn't matter what type of thing it is. If the function exists, you can call it. Do I have time to help you with your assignment? Depends on what the assignment is. Probably not, but what's the assignment? I might be able to give you some pointers. While I stare at this tensor product and try to figure out whether it's something that I can implement myself on a sparse matrix. Which I think the answer is probably not. It's probably also not necessary. Is unitary. Invert, we're always gonna have to use this. Okay, so I guess that was really the only one that makes it easy, or the only one that we can optimize easily. Let's just get status. Okay, I haven't done anything. You need to implement a class diagram with some functions and rules, etc. So, like, you have to print out on the screen, like, what classes are subclasses of others and what functions each of the classes has, something like that. I'm not sure what rules means in this case. Let's see if we're still hitting that Stack Overflow. Where was our Stack Overflow? It was quantum algorithm, and if this is 15, we were hitting the Stack Overflow. No, do I have Discord? I don't at the moment. Thinking about setting one up, but haven't done it yet. If you have the text of the question or something, you can paste it into chat. Although the bot that I have might become unhappy with you, but try pasting it into chat and seeing what happens. This test is working really hard. So, okay, so assuming that this is going to Stack Overflow, what do I think is Stack Overflowing is the question. I don't think the error message I got before is consistent with the call Stack Overflowing, and I'm not doing any recursion anyway, so I don't think it's that. Which is usually where Stack Overflows come from. So, the circuit has a vector of... The thing is, like, most everything that we're allocating is like heap allocated. It's mostly vectors. So unless the vector of pointers to things on the heap is so big that it's overflowing, which I'm not even sure if that can happen, I imagine it can, then it's a little bit hard for me to imagine that that's what's doing it. But I mean, the thing is that quantum circuits gates, quantum gate, vector of quantum gates, each of which is a matrix. But the vector is, all of these are heap allocated. In fact, yeah, there's no vector. It's not even multiple pointers that are pointing to the heap. It's presumably the vector has one pointer that points to the beginning of the heap. Okay. Couldn't allocate this gigantic thing. Oh, does that just mean that I'm ooming my machine? Being out of memory. Stack buffer overrun. Let's check. Calcutten says it's a picture, but it's depicting 3 classes in some banking system. Person, person register, and bank account. Okay. And you have to create those classes with the various functions, or do you have to actually, are you saying that you have to actually print out the class diagram? I guess you're saying you have to implement those classes. Oh, I should turn DMs on Twitter. Let me see if I can do that. Settings. How do I turn on? Actually, don't know how to turn on DMs in Twitter. Turn on DMs. Navigation, settings and privacy, privacy and safety. Direct messages. Alright, suppose I turn it on. Alright, there, DMs are on if you want to try again. Should be anyway. Yeah, implement those, and there are some functions with those. Okay, so they're kind of doing the object-oriented thing, where they're just trying to ask you to implement some classes and put some functions in place. So, I mean, what I can show you, and this will be useful, in general, I can kind of show you how that's done in Rust, and then which is basically the same thing, and I'll highlight some differences, and then you can see if you can generalize that to Java. But so, like, for instance, I have multiple structs in this quantum computing simulator that I'm writing. These structs are basically classes. They have some data, and they have this impl block is just a bunch of functions, a bunch of methods. So it's the same idea as a class. In Java, this would just be a class of qubits. It would have, it would contain within it some, are they called properties or members? I guess they're called members in Java. So it would have some member that's state of the type, unit vector, and then it would have some functions like a constructor, which is essentially what this new function is. Might have a few different constructors, and then would have some functions, some methods associated with it. So, like, I have an almost equals method for my qubit that knows how to check another qubit and compare it. And so qubit is one class. I have other ones like quantum register, quantum gate, and they have the same kind of thing going on. They have some members associated with them. They have some functions associated with them. Sometimes there's no concept of subtypes or subclasses in Rust, so don't have that. But that's like basically the structure. I don't know if I guess where are you getting stuck? Is it on the kind of macro, the top down, or is it on the bottom up actually implementing the functions? How to do deposit and withdraw. Well, so I don't actually see that you sent me anything. Maybe it's just slow to update, but typically what I would expect is that, you know, deposit and withdraw would be things that are so I'm looking at person register and bank account. So my guess is that a person is linked to a bank account. A person register probably registers people, and then a bank account has some dollar amounts in it. So I would have thought that probably a bank account can be withdrawn from or deposited into. So there could be a method on bank account that takes an amount and tries to add or subtract based on deposit and withdraw. And then if you need a person to be able to deposit and withdraw, the person can just delegate that to its bank account. So the person could, since they have a bank account, they can call deposit or withdraw on it. I do not see what you sent. No. Maybe Twitter's totally borked because of the ongoing drama. I don't know. Yeah, I don't see anything there. Okay. So this thing ran. Oh, and then it buffer overflowed. So I was going to shoot. Where did my status stack buffer overrun? This doesn't look like a Rust thing. This looks like an operating system thing. Okay, so this is basically an is what I'm being told by the Google. So I think it's not completely impossible that I'm actually ooming my machine, but I don't think it's likely because I have a lot of memory. That said, and it's ooming on what? It was ooming on this step. I wonder if it's ooming on inverting this matrix. Because it runs on smaller ones. Let's see if we can tell. Drill in here. Drill in here. So capital N is, or 15. It's going to be 8 qubits. So 2 to the 8 times 2. So 2 to the 9. And it's able to instantiate the matrices. And then I expect the inverse Fourier transform step to take some time. Oh, I got a message request, maybe. Are you, 123 Honky Donkey Calcutten? It's a pretty different name than the name you've got there. Ah, looks like it is. Okay. Yeah. Add account, find account, calculate total balance. What am I looking for here? Deposit and withdraw. Okay, so this is about what I would expect. So your bank account has a member in it that's the balance, right? That's the amount in your bank account. So your deposit function should just take an amount and update your balance to add money into it, right? Money was the amount is the money you're putting in, and the withdraw function should subtract money out of the balance. Is that what you're trying to do? Okay, so this is still hanging on the inverse Fourier transform. Okay. So the issue is we're trying to invert a matrix that is 2 to the 8th. And that's taking forever and eventually ooming our machine. So we kind of suspected that this might be the issue. And so what we should be able to do is, instead of implementing inverse Fourier transform as just the inverse of a regular Fourier transform, we can implement it analogously to this. I guess we're trying to invert a bunch of matrices in here. Calcutten says it must not be possible to withdraw money on an account with a negative balance. You may withdraw a maximum of 50% of the total balance at one time. Okay, yeah, so this gets into one of the things I don't like about Java that I do like about Rust, is that in Java, like, those functions are, the return type is void in your class diagram for deposit and withdraw, which means you're not returning anything. And so when you deposit, what does it mean for you to not be able to do something if you're not returning something? And my guess is that it means you have to throw an error. You have to throw some sort of exception. within Java, which you can do if your return type is void. You're not allowed to do that in Rust. Hey, it's Pawnman. How you doing, Pawnman? We're doing some optimization, some more optimization on our quantum simulator, and we're also chatting with Calcutten here, who's working on some Java homework, and trying to help him out there. Calcutten hates Java. Trying to reverse a string in Rust. It's a good thing to want to do. There are some, well, I won't give you any hints unless you asked for them. Calcutten, have you talked about throwing exceptions in Java? Pawnman says, yeah, no hints, lol. Yeah, okay, I'll keep my mouth shut. Okay, let's do inverse Fourier transform better. So we're just going to, let's do it here. We'll do a partial inverse Fourier transform. We will start with a new qubit. We will add the Hadamard gate at the very end. And then let's see here. Does it matter the order that we apply these in? I think it might not matter. I think I might just be able to rotate this by a negative number, and it might not matter. And I wonder if I have to rotate the input qubits around. I'm honestly not sure. I'm kind of hoping that we can just throw some code in here and then see if our tests pass, which is like maybe not the best thing to be doing, but inverse Fourier transform is going to use the partial inverse Fourier transform. It's going to do a gate at the end, which is a reverse permutation. And which I have to check the implementation of that also. And then there's a question about these indexes here. But let's see. Let's see if this is sufficient. I'm pretty sure it's not. Fourier transform is Fourier transform. Yeah, okay, fails. And sure. Okay, let's go ahead and visualize that. And let's use 3 qubits. 3 qubits. And cargo. This is a regular forward Fourier transform. I just want to remind myself visually of what it looks like. Okay, so permutation first, then Hadamard, rotation, rotation, Hadamard, rotation, Hadamard, and we're done. Okay, so we expect, for the inverse, we expect Hadamard, rotation, Hadamard, rotation, rotation, Hadamard, and then we're done. Pawnman says I could use help to find the intersection between two exponential functions using natural logs. Yeah, that's a thing you can do. Is that a thing you can do? Probably. Sure. What do I do for work? I have been an actuary and I've worked at a software company. At the moment, I don't do anything for work because I had a kid recently, and I am taking some time off to take care of him and doing this as a side project. I have a math background though, so my background is more like, I will not claim to be the greatest coder in the world by a long shot. I use programming as a tool, as a way to understand things or work on real world problems. So really, my intent here is more to come to understand quantum computing and like help other people understand what's going on, and use programming to like keep me honest. Because if I just stare at this stuff all day long, I do not keep myself honest. I have a math background, but if I'm working through all this crazy math, I will make mistakes. I will convince myself that I understood it. Whereas if I do it in a Rust program, it's not going to be right until it's right. So it helps keep me honest, and it helps teach me new and complex things, and hopefully can help teach other people also. Congrats, man. Oh, thank you. Yeah, it's been awesome. My son is almost 5 months old now, and he's the best. Okay, so let's take a look at the inverse Fourier transform. Okay, so we have permutation up front. That's immediately wrong, right? That's just immediately wrong. I think I might not have clicked save because I don't remember compiling. Okay, there we go. Okay, so this is wrong because we should have a Hadamard at the end, yeah? Or rather, a Hadamard at the beginning. I feel like I'm missing... I feel like this Hadamard is meant to be at the beginning. Fourier transform. Partial inverse Fourier transform is the first thing that happens. It does not start with Hadamard, and I think it should, right? Fourier transform. Looking at the book for a moment. Yeah, it should start and end with Hadamard. So permutation and partial Fourier transform, and each of those starts with a Hadamard. Where's the Hadamard that it should end with coming from? Oh, this loop trivially doesn't run once. And that gets us the last Hadamard. Like how I wrote this code, and I still don't remember what it does. Okay, so maybe we keep the Hadamard at the beginning. Let's put it up here. Let's just, I don't know why I'm trying to do this in my brain. Let's do this on paper. Inverse Fourier, or regular Fourier transform. Run this thing. I'm pretty sure it's, here we go. So it's permutation, Hadamard, on 0 and 1, rotation, rotation of 1/4, rotation of 1/8 of somewhat different gates, but we'll deal with that in a minute. Hadamard of 0, 2. Rotation of 1/4. And Hadamard of 0, 3. This is the Fourier transform. So we expect the inverse Fourier transform to be just the reverse order of this with gates inverted, but Hadamard gates are self-inverse. So this would be permutation at the bottom. We'll say inverse permutation. Hadamard 0, 1. Rotation by -1/4. Rotation by -1/8. Hadamard 0, 2, because it's its own inverse. Rotation by -1/4. And Hadamard 0, 3. Wait, there's something weird here. There is no 0, 3. There are only 3 basis components. 0, 2. That's 0, 1. Is this 1, 2? Oh, Hadamard is a single qubit gate. That's why. So this is just so all of the Hadamard 0 somethings should just be Hadamards. Replace with this. I was trying to learn Vim this morning. It was really fun, but I won't torture you guys with watching me struggle through Vim. Okay. And then this is just 2, 1, 0. And 0, 1, 2. Okay. So this is what we want. Let's find out what we're getting. Inverse. And cargo. My terminal is dead. My terminal is dead. My terminal is dead. Cargo run. Calcutten says, how am I supposed to find the solution on how to create these methods? Well, trying to think what the... So you know how to... So if you forget about those extra rules and you're just... The account balance is some number and it can be positive or negative, and you want to adjust that number by the amount that you're depositing or withdrawing, do you know how to do that? Like forgetting about the like business logic. Okay, so this is immediately wrong. So we need to do some things with our indices. But Hadamard, rotation. Hadamard, yeah, and these are wrong also. Okay. Where was I? I was in quantum circuit. And so so we need Hadamard. This needs to be a Hadamard 2 here. So we can say n qubits minus start IDX. And then we need to go through these in like the opposite order. Okay, well, let's go ahead and cargo run this and see if we've gotten closer. Public void deposit double amount balance plus equals amount. Yep, that looks right. I think you're missing a semicolon, but I know what you mean. And I don't know. I'm not a Java person, so. But yeah, that looks right. So then the other constraint that you've been given, which is in your function signature, there is that it returns void. So it returns nothing, but you have to disallow certain behaviors. And if you want to disallow certain behaviors, I imagine that means you're going to have to throw exceptions. Because otherwise I don't, unless like your two options to disallow those behaviors are one to just silently not do it, right? So if you try to deposit, or if you try to withdraw $100 and you have negative $5, you just don't withdraw anything. But that seems, certainly in a real world system, that seems awful, because now you're silently changing the behavior. Like, it's just not doing what you think it's doing. You've given no feedback to the caller about that. So I think more likely you want to throw an exception when that happens. Yeah, your getters and setters, can have that logic in it, but they also can't return, or at least the setter probably doesn't return anything, right? It also just sets and returns void. Have you done exceptions in your class? All right, let's find out why my code didn't compile. It's because I changed something and broke it. N qubits minus start IDX minus 1, yeah. Seems this looks suspiciously like the right answer. Ish. Sort of. Potentially. Not quite. But it's better. Okay, so this was the correct gate. The problem now is that we expect to have just the one rotation of -1/4 instead of both of these rotations. So let's figure out the rest of the loop. So instead of going from start IDX, which is going to go 0, 1, 2, we need to go from, let's see here, so that's going to go 1, 2, it's going to just go 1, 2 in this case, and then trivially exit. So we instead need to trivially exit the first time. This also feels like code duplication, which I'm not super thrilled about. See here. So I wonder if maybe I want to. So another possibility here is to reverse it outside the function. IDX. Yeah, because it's really the end IDX that we want now. I think. Let's see. So in the regular Fourier transform, what's getting rotated by how much? So it's a half, or a quarter, an eighth, and a quarter, and it's the third, the second, or the 2 to the 2 qubit, the 2 to the 1 qubit, and the 2 to the 0 qubit. Okay. So this is the 2 to the second qubit, 2 to the first cubit and the 2 to the 0 cubit. And so I just want to create this same pattern going the other way. I think it is going to be easiest if I do my circuit, if I add my Hadamard gate at the beginning. No, at the end. It's going to be easiest if I add my Hadamard gate at the end, which is the reverse of what I did before, so that's kind of nice. And then we want to go from n qubits to n qubits, n minus 1, n qubits minus 1 to n minus 2 to n minus 2 to n minus 1 to n. So this should be n qubits minus start IDX. Yeah, and then it trivially skips the first time around, so we'll get Hadamard at the beginning for free. Plausibly good. Believe that that might be correct. I think it's possible. Okay, and we're on the Fourier transform. Overrun. This looks correct. This looks correct. Okay, and now let's cargo test and see if it is. How would I convert, say, 5 times 2 to the 2x? Where your, can you put more parentheses on that? Is the, I assume that the raised to the, it's raised to the 2x power. So it's 5 times, so it's 5 times 2 to the 2x, like that. So if you take the natural, I don't know what to log form is exactly, but I imagine, because different people have different terms for it. But if you take the natural log of that, what do you get? Would be my question to you. Okay, bunch of tests failed, so I did not do this right. Kind of looked like I did it right. I was kind of proud of myself a minute ago. Let's compare. Okay, so first, oh wait. Why is there a permutation up front? Permutation should be at the end. No, I disagree. I disagree with you're close, but it's not quite right. So remember that you're wrapping the whole thing in a log, right? It looks like that. Did I miss a parenthesis? No. And so your 5 does not remain. You can't just pull the 5 out, right? Natural log isn't linear. So you don't just get a 5 out in front. You did it right on the inside parentheses, but you didn't quite do it right on the outside parentheses. Let's see. So if you've got this, right? So logging products makes them into sums. So you're going to get ln of 5 plus ln of 2 to the 2x. Right? And then you're going to keep working from there. So the thing to know, the thing you should think about when you think about taking the log of something is that it turns products into sums and divisions into differences. So then I think you got the rest of it. I mean, this is going to be, so this is 2 to the 2x means you've got 2 times 2 times 2, all that. 2x times, right? That's what it means to have 2 to the 2x. There are 2x of these 2's, and so I think you correctly wrote down that you then get to pull the 2x out of that, and you just get ln 2. And I would consider this fully simplified. I mean, I would probably write it in the other order. Or even, I would probably write it 2 times ln of 2 times x plus ln of 5 is probably how I would write it. Because this is just linear in x. And you can't really simplify this down. So I imagine this is what they mean by log form, but I don't know. Damn, that makes so much sense. Yeah, I don't think logs are taught very well. The thing that they should teach you is that it turns products into sums and divisions into differences, right? So like if you had a different example that was like ln of, I don't know, 5 to the 3x over 9, then this is ln of 5 to the 3x minus ln of 9, right? Because the division got turned into subtraction when you pull it outside. And I guess the other thing I would say, and I don't really remember, I mean, I sort of remember that this is true. The way it's easier to remember, for me at least, is that exponentials turn sums into multiplication, right? So if you have like e to the 2 times 4, this is e to the 2 plus e to the 4, right? Or e to the 2 or whatever. 7 to the 5 minus 3 is 7 to the 5 divided by 7 to the 3. And so if you know that if you think of taking a power, if you think of raising something to a power as turning sums into boy, did I not write that right? That should be multiplied by turning sums into products and turning differences into divisions, then, and you know that natural log or any log-based something is the inverse function, then you can remember that logs turn sums into products and differences into fractions. Yeah, not a big fan of how that's taught in the US, at least. Okay, so I was gonna check. I was gonna double check what my circuit looks like. So, oh right, why do I have a permutation up front when I should have a permutation at the end? Was my question. So circuit permutation Isn't this at the end? Oh, it's because I have the Fourier transform in here. All right. I got excited there, but I did it wrong. Export rust backtrace is 1. Oh man, am I not allowed to? I'm using a new terminal that's called New Shell. It's a Rust-based terminal, and I don't know how to do. Export doesn't do the thing I want it to do. I think I can do like this though. Interesting. How do I set an environment variable in new shell environment variable? Set environment variable let env. So if I do let env rust backtrace equals 1, doesn't like that. Do I need spaces? Okay, and now if I try this again, it dies, but I get my full backtrace. Okay, let env, interesting. All right. Okay, but broadly speaking, the issue is that, yes, this is fair. Okay. So these need to be, so these are going, this should have been a 1. 2, 1, 0. Are the rotations, but it's a controlled rotation. Is it 2, 1, 0? Go back to the Fourier transform. This looks like 2. These are 2-qubit gates. So this is let's just look at the circuit diagram. I can make myself crazy for these things. Sheesh, great explanation. Thanks. Oh, for sure. I'm glad that's helpful for you. Yeah, demystifying math education is a thing I would like to do. So, stoked if I can do that a little bit. Okay, so in the circuit diagram for the Fourier transform, we're always using the start IDX and controlling based on each individual qubit. So now we always want to be controlling based on start IDX. And then we want to walk through the rest of them. So, and we're going this way. So it should be 0, 1. So we should start at the end, which is not what we're doing. But we can do that by going n qubits minus I minus 1. And that would be starting at the end. So for the very first, so the first one will be trivial. The second one is going to be just 2, for instance. So then 2 would be controlling 3 minus 2 minus 1. That's not right. It's just n qubits minus I, isn't it? These off by 1 errors are so finicky. Inverse. Run. Need a build script for this. Fails. Y. Same story. So if start IDX is 0, then this is trivial. If start IDX is 1, then we go from n minus 1, we just have n minus 1 qubits. Start IDX is -1, or is n minus 1, and this is duplicative. So yeah, -1. I was right the first time. Okay. So now we have the, so it's still not right though, but we have the permutation gate at the end, which is good. We have Hadamard. Okay, so this one needs to be this one. We're so close. Pretty sure these are correct. I think. Except this needs to be a quarter. With the right number of things going on. Which is good. To the K. My cat needs to escape. Hopefully, oh, my cat just went and hid under the bed, so maybe not. Okay. So K should not be increasing. K should be decreasing. So K should be n minus 1, and K should be decreasing, I believe. N qubits minus 1. Okay, so this is a quarter, this is a quarter, this is an eighth. No, this is an eighth, this is an eighth, this is a quarter. But this still isn't right. It's not n qubits minus 1, because that should be a quarter. It is n qubits minus start IDX. Just gotta start at n minus 1. So n minus 2. Because I add 1 up here. Nope. It starts at n minus 1. Can I just get rid of... No, that's actively wrong. N cubits minus 1 is not where it should start. It should start at n minus 1. N minus start IDX. Maybe minus 1. Probably minus 1. I'm tired, so I'm not using my brain. Plus 1. I should start using my brain. But it worked so well to not use my brain. No, it didn't. This is still wrong. This is still wrong. So when start IDX is 0, gets skipped. When start IDX is 1, then this is 2, and we want it to be 1 over 2. We want it to be 1 over 4, which is R2. So it's like this, no? But this fails because somewhere in here we're doing a thing we're not supposed to do. Because we end up subtracting off too many K's. Do we not want K to decrease? 1/4, 1/8. No, we do want K to decrease. Oh. But K is going negative somehow. N cubits, fine. N cubits minus 1. N cubits minus 1 is 2. And when it's 2, we want K to be 2. What was the one that I got working? One of them worked. This one works. But the problem with this one is it's going in the wrong order. It should start, it's starting at 1 over 8 and then doing 1 over 4. It should start at 1 over 4. Which this would... Let's see here, for this to start at 1/8, this would need to be 3, K would need to be 2, and that would be the case where start IDX is not 0, not 1, but 2. So K is just equal to start IDX here. There we go. Yes, okay, that looks correct. This is still wrong. But okay, because now this is 1/2, 1/8, 1/2. And I see the issue is I'm pretty sure the gates these are being applied to are switched. So 1/4, 1/8, 1/4 is good. I think I said 1/2 and 1/4, but I meant 1/4 and 1/8. This is getting applied to 2 to the 2, which is right. But these are counting in the wrong order. So hopefully last but not least, so the point here is that rather than doing to the 0 to the 1, so this is when start IDX is 2. So everything is on the second qubit, on the 2 to the 2 qubit, and then we're doing going down the list, and instead we want to go up the list. So we want plus I. It's got to be n qubits minus start IDX plus I, or whatever the version of this is that works. Start IDX. So start IDX is 1, then this is 1, this is 2, we need that to be plus 0, right? So we need to do -1 here. Maybe. Nope. Again, I'm just going to try a couple of these in case the off by 1 error. It's not so bad. Start IDX. Look at my circuit diagram. So start IDX is start IDX is 0. Oh, now my cat actually needs to get out. The joys of cat ownership. Exceedingly close to this being the right answer. So it needs to be, first time it runs, this gets skipped. The second time it runs, it needs to be 0 and 1. Yes. So start IDX minus 1. And then so this is 1. So this is 0. This needs to be one also. No. It needs to be 2. This is 0. It needs to be 1. So then this is 3 minus 1 is 2. So minus 1 plus I. Still no. Oh, but it's failing on not being able to do reverse permutation. Partial inverse Fourier transform. Oh no, it doesn't. Yeah, it doesn't like this. And it doesn't like this because I got it all the way up to 3. And Cupid's minus start index. It's going to be 2. Minus 1 is 1. Plus 1 is 2. How can it be minus 2? I don't know where 2 came from in here. This is like aggressively not the nicest algorithm I've ever written. Attempt to subtract with overflow. Yeah, I don't think it can be minus 2. What is K in this circuit diagram? So when K plus 1 is 2, gets to be on the second one. Oh, I get it. I get it, I think. It needs to hang on. Previously we were doing I up to the start IDX. So now shouldn't we need to be doing the start IDX down to something? Seems like yes. Something that starts at 0 and counts upwards. So like K minus the start IDX. No, starts at 0. Starts at 0 and counts upward. So n qubits minus start IDX. So I minus n qubits minus start IDX. Because that way it counts upward from 0. Hey, okay. Answer still looks wrong. So this is a quarter, an eighth, a quarter. Is that what we wanted? Quarter, eighth, quarter. Good. And then it's the big split, the small split, the smallest split, which I think is correct. So what's that about? Visualization. And let's just card a test for kicks. I know it's wrong though, because the answer didn't look right. Yeah. So in our Fourier transform, oh, it's the small and then bigger and bigger. Oh god. Okay, so it has to be the big split and then smaller and smaller. Which it is. It's the big split and then smaller and smaller. So doesn't this look correct now? Something wrong with my permutation, maybe? Let's get rid of the permutation. For a moment. Hey, Susie. Woe is this wizardry? It is not wizardry. It is an attempt to implement or, simulate a quantum algorithm in a classical computer and visualize that. So, so basically, when you think about like what a computer does, it's taking ones and zeros and modifying them with circuits. So the same thing is true of a quantum computer. Here are your ones and zeros that you could potentially put in as inputs. So 0, 0, 0. I'm using 3 qubits, basically 3 bits as an input. So you could put in 0, 0, 0. You could put in 0, 0, 1, 0, 1, 0, and so on, all the way down to 1, 1, 1. In this case, I've put all of the difference between a quantum circuit and a regular circuit is that you can have mixed states. So you can have qubits that are interfering with each other, that are in superpositions. So in this case, I put in a pure, all of the probability weight is behind 0, 0, 1, and then I put it through this thing, which is really just a matrix. It is it's a particular gate called a Hadamard gate being applied to the top, the leftmost qubit here, and what it does is it creates a superposition of the qubit you put in and that same qubit with the bit flipped. So in this case, it's the leftmost bit, so it would be this qubit 001 with the 101 qubit. And so you can see in the result, now we have half of our probability on each of those two. And we continue. And we're trying to implement the inverse quantum Fourier transform. We already did a regular Fourier transform, and previously I just inverted it, but it turns out to be very, very slow when we do big circuits. So now we're directly implementing the inverse quantum Fourier transform, which creates this pretty colored thing at the end. But this is wrong. What it's kind of meant to look like is what we have for the regular Fourier transform. It's kind of meant to look like this nice rainbow thing at the end. Basically what this is saying is it's now a complete superposition of all of the different states that the computer could be in. But the different colors correspond to rotating the coefficient by some amount. And so we've now encoded the one basis factor that we put in, the original state, into this superposition as the difference in the rotations of each of these. And so you can kind of see it walks through the rainbow. The rainbow corresponds to the different rotations. They're, sort of, we would get all the way back around if there were one more qubit here. So it'd be nice if our inverse Fourier transform and our Fourier transform were inverses of each other. That's kind of what we would need them to be, but they're not at the moment, because I have some subtle little bug that we're trying to track down. So in particular, you can see that we're getting back to the same color we started with immediately, rather than kind of stepping through the rainbow, which we don't want. Hopefully that's a reasonable, quick explanation of that. Okay, cool. So I think the circuit looks how we expect it to look. I removed the permutation that we do at the end, and it doesn't really seem to have done anything. I mean, it did something, but it's not, I don't think it's a problem with the permutation, so I'm going to go ahead and put that back. And so, where are we going wrong? And just to check, I'm just going to move this up to the top and do it up front first. Whoops. It's going to work. Yeah, it doesn't work. And if we do a regular permutation, I also expect this not to work. But there's a weird thing here where some of these gates are invertible, and so yeah, also doesn't work. Okay. And so like you can choose whether you want to reorder them or reverse them. But that doesn't seem to be the issue here. So where are we going wrong? Just gonna screenshot this and put this side by side, I guess. So this is the inverse. And then this is the actual. Anybody sees where they're not inverses? I know they're not showing on the screen yet, but I'm not the most visual person in the world, so I will put them on the screen in a moment. Snip, 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 and oops. So do this Fourier. All right, what's the easiest way to put both these on the screen? Fourier is this one, and inverse is this one. And okay. So we expect these to be inverses of one another. So the top one's the actual Fourier transform, the bottom one's the inverse. So this and this are exactly the same matrix, but that's fine because it's its own inverse in this particular case. These are exactly the same matrix, which is fine because Hadamard gates are their own inverse. Same with these two, same with these two. Okay. These are not the same matrix. These are not inverses of each other, so this is the inverse of this. And this, and this. Okay, so that's our issue. That is our issue. So this is, I think this is 0. Let's see here. So in the regular Fourier transform, yeah, so this one is 0, is the 0-1 rotation gate by a quarter. We need it to be the 0-2 rotation gate. Circuit. So everything else is the same, but instead of being I guess we need it to be the 1-2. Yeah, we need it to be the 1-2 or the 2-1. They're the same thing. So when start IDX is 1, then this is 1, and we need this to be 2. And when start IDX is so this isn't really right, obviously. We need it to be 1-2 the first time, then we need it to be 0-2, and then 1-2 the second time. Be 1-2 the first time, and then 0. No, and then 1202 the second time. This is 0, 1, 0, 2, 1, 2. 0, 1, 0, 2, 1, 2. That's what that is. And this, so this has to be 1, 2, 0, 2, 0, 1. Okay. And so this should be n qubits minus, this needs to count down from n qubits minus 2 from n qubits minus 1, right? So this is going to have a minus I. That's something we definitely know. And then it's going to start, this is the innermost loop. Needs to start at, so this is going to be when start IDX is 2. So it needs to just start at start IDX. No, it just needs to start at n qubits minus 1, no matter what. N qubits minus 1 minus I. And then the other one is the outer loop. And so that's going to be just start IDX. No, it's not. It's going to be, it counts down. So it's going to be n qubits minus 1 minus start IDX. Because here, start IDX is going to be 2. So 3 minus 1 is 2, minus 2 is 0. Here, start IDX is going to be 1. So 3 minus 1 minus 1 is 1. Realize this is not the most fascinating thing to watch at the moment. Okay, this is the Fourier analysis, though. Fourier transform, rather. So let's make it inverse Fourier transform. And dies because surely I did it wrong somewhere. And cubits minus 1 is always 2. If I subtract start IDX from each of those, I go 2, 1, 0. That is true. And then I want to count down always from 2. So that's n cubits minus 1. And then we count down. But it's not from I. I need this to be I minus n cubits minus start IDX. There it is. Awesome. Okay, that's what we're looking for, because now we're starting, if we remember our complex numbers and we look at our legend, we expect to be rotating by an eighth of the circle every step here, and that would be red, yellow, yellowish, well, red, orange, yellow, green, light blue, dark blue, purple, pink, red. Except we go in the other order because it's the inverse Fourier transform. So red, pink, purple, blue, light blue, green, yellow, orange. Incredible. Okay. And I imagine this simplifies somehow. N cubits minus n cubits. Nope, it absolutely does not simplify somehow. That's gross, but okay. Let's cargo test. And all of our tests that were passing before pass now, which is great. And we still but we way faster. So we have successfully sped up our path to ooming, our path to running out of memory. Okay, I am gonna call it there. I need to wrap up, and I feel like this is a sufficient, albeit maybe Pyrrhic victory. Speed up inverse Fourier transform by building it from scratch instead of inverting. And next time we will get back to figuring out why we're still ooming. Doesn't really seem like we should. I can't help myself. I'm going to just step through this one time before we go. Step. All of this works fine. Why is that inverse Fourier transform so slow? Didn't I just optimize the hell out of it? Kind of seems like yes. Okay, so here is where we started hitting issues. Okay, the tensor product. Okay, so the issue is when we try and do this tensor product, it ooms. Fascinating. Okay, so my guess is that next time we're going to have to figure out a sparse matrix algorithm for tensor product. which seems very plausible, because it's kind of the same idea. I just have to remember. How to put together tensor products, but that's what Wikipedia is for. Cool. So we will start there next time. I might stream tomorrow. Tomorrow is Thanksgiving in the U.S., so it's a little dicey. We're having a pretty quiet Thanksgiving, so I'm gonna try to stream, but it's not certain. If not, I'll probably stream on Friday. Hope everybody has a good rest of your day. Calcutten, hope you got your Java homework sorted out. Pawnman, I hope logarithms are a little clearer for you. And Susie, I hope it seems slightly less like wizardry now. All right, take care. Have a good one.